In this video, we will be reviewing the instructions for practice 5, which will be to calculate both exact and estimated percentiles, and then compare how these are different, because we know that there are differences based on distribution shape, right? So when we estimate a percentile, z-scores are based off of a normal distribution, versus exact percentiles, we just want to know where someone or where a certain value might lie just based on the data that we've collected. So there will be discrepancies that you might see between exact and estimated percentiles. Generally, your value should be the same, especially if you have done your normality test and you can assume that your data are normally distributed. But sometimes that's not always the case. And so if you wanted to know someone's percentile as it might pertain to a population, estimated percentiles would probably be the way to go. If you wanted to know somebody's percentile just based on the sample they were collected in, the exact percentile might be a little bit more precise for what you're looking for. In our data set, we are going to be calculating the exact and estimated percentiles for a person who has an output at 1,000 watts. So we can go to our data set and see that we've got some power data collected. This is organized just because there's a lot of values, so they've kind of been smushed into one lump. So this is going to be our entire set of data. We'll create an area for our exact percentile calculation. Okay. And we know for our exact percentile, we need our cumulative frequency and our sample size. So my advice to you guys is when you're going through these steps, think about what are the variables I need. And the easiest way you can create your checklist is to make a list of the variables that go into your equation. So for this one, our raw score we need to know, which is 1,000. The cumulative frequency we can find by doing the COUNTIF function. And I want to know how many people are in this range that have a power output less than or equal to 1,000. So that'll give me how many people performed at or worse than my raw score of interest. My sample size is simply going to be the count of my data. And then based on these two values, I can calculate my percentile by doing the cumulative frequency divided by the sample size multiplied by 100. And then we can always change this value to reflect 2 decimal places. And we can see a value of 1,000 would be at the 64th.34 percentile. That was not very eloquently said. Then, if we wanted to do an estimated percentile, we are operating under the assumption that our data are normally distributed. So when we do estimated percentiles, we use our z-scores, right? So if you think about our z-score formula, we have x, the mean, or x minus the mean divided by the standard deviation. And then based on our z-score, we can figure out what the associated percentile is on our z-table. So again, our x is still, or raw score is still 1,000. The mean we can easily calculate by typing average and finding the average of that range of data. Same thing with standard deviation. We've used these functions before. And then same thing I'm going to make, just because I have OCD, I'm going to make those to 2 decimal places. And actually, I meant to type Z. I said it, but I didn't write it. Our Z-score is going to be our raw score minus the mean divided by standard deviation. So then I can see I have a Z-score of 0.29. I can go to my Z-table. It was a positive Z-score, so I'm going to be on the positive Z-table. 0.2, we're in this row, and 9 will be at the very last value. So in this one, the percentile or probability that I would randomly select somebody who had a power output of 1,000 or less would be 0.6141 or 61.41%. So then I can click here and insert my percentile of 61.64%. Now we do notice there is a small percentile discrepancy between the estimated and the exact percentiles. So let's visualize our data. If we highlight all of our values, and let's insert a histogram, since we know that's one way we can evaluate distribution shape. Okay. We notice in our histogram, scroll down just a little bit, that our data is slightly positively skewed. So if I adjust the number of bins, we can go up or down, right? And it becomes a little bit more and more likely that there's potentially an outlier value to the right of the mean. For the most part, we fairly look normal when we've got less bars, but there's a possibility that we've got some skewness going on here. Right? We can assess this visually. We could also do our z-score calculations. So, sorry, I want to move this out of the way. If we did our sample skewness, standard error of skewness, and our z of skew, since visually we can kind of see this is what's going on, right? We can use our skew function on our data, calculate our standard error. So that was the square root of 6 divided by n. So count our data, double parentheses. And then z-skew, again, is just our sample skewness divided by our standard error. And we get a value of 3.16. So in this case, 3.16 is greater than our 1.96 criteria cutoff. So based on this calculation, as well as a visual representation, it's likely that our data are skewed. So why is it that we get this difference in percentile values? I'm going to move over and draw for you guys instead, just to kind of give an idea of where we are here. So when we plotted our actual data, we've got something that looks more along the lines of this, where our mean is shifted or drawn further towards the left from where we might think it would be based on the peak, because there's an outlier, likely there's an outlier out on the right end of the distribution. So in our case, our mean gets dragged to the right. And in our estimated percentile, we have the assumption that our data look like this, right? It's a horrible normal distribution, but you get the gist, okay? But we have this idea that the mean is centered where the peak of our distribution is, and there are equal percentages of values on both sides of the mean. So in this normal distribution scenario, we said that 61.64% of our data are going to lie below 1,000. If we take note of what our mean is, that's 949. 1,000 would be just above that mean, right? It's still between the mean and 1 standard deviation, so that's what this is. This is referring to x, which was 1,000. Okay, and the percentile that I end up calculating is going to reflect all of the data that are to the left of this point. So when our mean is perfectly centered in the middle of the distribution, there's 50% of the data should be to the left of the mean, 50% should be to the right. And so if we're just slightly to the right of the mean, it's 50% plus a little bit more, which ends up giving us our 61.64%. However, when our mean is not aligned with the peak of the distribution, and we're still saying that if we're just past the mean, right, where the x is still equal to 1,000. Hello, there we go. Okay. And we still want to know the percentage of values that lie to the left of that. We can see that because our data are skewed, more of our distribution, or a greater percentage of our distribution, lies on this left side of the mean. So we don't have an equal 50% on one side and 50% on the other side anymore. There's a greater percentage on the left, which is why when we calculate an exact percentile based on the actual distribution shape, which is slightly positively skewed, that's why we have a larger percentile that shows up, because there are actually more values that are clumped over in this area because the mean was dragged away from that central peak. So it's important when you're calculating percentiles, you understand what you're looking for, right? Are you interested in someone's percentile within the exact sample they were calculated in, or do you kind of want to know what their estimated percentile would be if your sample was representative of the population? So when we do estimated percentiles, we assume that we have a normal distribution. When we do exact percentiles, we kind of just have to go off of whatever the distribution shape is that we have. And then we just need to be mindful how that distribution shape might affect the percentile value that we calculate.